Hello everyone, welcome back to Module 2 of the AI Ethics curriculum presented by the AIE team here at Shift SE. In this module, we're going to be talking about bias and fairness, covering a little bit more in depth about the overarching concept of this module. You guys met me in the previous module. My name is Montej. I am a senior here at the University of Southern California, majoring in computer science.
Hi, I'm Ada. I'm majoring in computer science and business administration, and I'm a sophomore at University of Southern California. So today we'll be covering the definitions for bias and fairness, and then we'll go into more detail about fairness metrics. And then in terms of fairness metrics, we're going to cover demographic parity and individual fairness. And then we just want to elaborate more on why do these concepts matter, and just kind of wrap it up with sampling bias. So let's talk about what bias and fairness mean within the context of AI. Bias refers to the systematic errors or prejudices in AI models that result in unfair or unbalanced outcomes, often due to skewed data, flawed assumptions, or design choices. And fairness, on the other hand, in AI refers to the absence of any prejudice or favoritism toward individuals or groups in algorithmic outcomes. So fairness ensures that no matter, regardless of your background, the algorithm will produce similar or the same output. And this means that ensuring that AI systems treat similar individuals similarly and do not systematically disadvantage any particular group. So we have a small diagram that is aimed at basically explaining this relation, where we have human bias in society already, and that affects culture, and culture creates discrimination, and this discrimination is one way or another passed into the AI systems, just because the data we train AI systems on could also be biased. And if we do not fix these discrimination codes embedded in society, we can never produce AI systems that are not biased. So we're just gonna go over today how we measure fairness in AI systems, and for that we use fairness metrics.
So what exactly are fairness metrics? You can think of them as tools that researchers, analysts, and engineers use to measure how fair an AI system is, which comes in very handy when you're dealing with different individuals, groups, and data sets that are already diverse. The whole goal is to make sure that the model predictions are as equitable as they can be. One real-life example is a LinkedIn AI algorithm suggesting the same jobs to different demographics. In this module, we're going to cover two main fairness metrics, the demographic parity and individual fairness. Demographic parity means that a model gives positive results, like approvals, equally to different groups. For example, men and women should have the same chance of being approved. It doesn't matter if one group is more qualified, the model only cares about equal approval rates. So if 60% of men are approved, then 60% of women should be too. A demographic parity difference close to zero means that the model treats groups equally. It's calculated by subtracting the approval rate of one group from another. But there are some downsides. It doesn't check if people are actually qualified, just that approval rates match. This could mean approving someone unqualified just to balance group numbers. It might also hurt accuracy, like rejecting qualified people from one group to even things out. If used the wrong way, it could lead to unfair outcomes in the other direction.
After talking about group fairness, now we're going to talk about individual fairness. And individual fairness refers to the idea that similar individuals should receive similar outcomes from an algorithm. So looking at the slides, if we have two individuals, xi and xj, and where d is a task-specific similarity metric between individuals, the distance between these two individuals should be closer to zero if fairness is the case. So if the difference between these two individuals within the context of algorithm A, that means that the algorithm is not fair enough. And an example of this could be, for the task could be a credit score and income or debt to income ratio. And the prediction could be a loan approval, for example, where two different individuals should be receiving similar loan approvals based on the algorithm. Another example of this could be college applications, where let's say you're building a platform for college applications and two students with similar GPAs or SATs should not be getting different admissions based on, for example, wherever they live, which could be determined by the zip codes they enter to the system. So if one is accepted and the other one is rejected, individual fairness may be violated, even if acceptance rates across regions look balanced overall. Just like any other method, there are some limitations going into the individual fairness process too, where defining similarity could be tough for each individual in the group. For example, what makes two people similar for a task, or how do we choose the right distance metric, D? Or that could be there's definitely a high computational cost comparing it to the group fairness. So it really comes down to what type of data set you have, or the sampling size you have for the algorithm you want to use. And there's definitely trade-offs with group fairness too. You can satisfy one but violate other. For example, making decisions to balance group statistics might mean treating some similar individuals differently as opposed to the group fairness.
Let's take a look at this table. Group fairness looks at how groups are treated overall. For example, it checks whether men and women get similar approval rates. It's easier to measure, but can miss unfair treatment of individuals. Individual fairness focuses on treating similar people similarly. It's more precise and protects individual rights, but it's hard to measure because it needs a good way to define similarity. In essence, group fairness is about equal treatment across groups, while individual fairness is about fairness for each person. Why do these concepts even matter in the first place? Well, it comes down to one big thing. AI is now being used to make critical decisions all over the industry, like who gets a job, a loan, or healthcare. That's why it's important for AI to be trained on diverse and fair data. In the past, we've seen real problems when it comes to hiring tools, rejecting underrepresented groups, criminal justice systems having shown racial bias, and healthcare AI and facial recognition systems also missing the needs and failing on non-white faces. If we don't address bias, the technology we create will only work well for certain groups, leaving others behind. This image shows a lot of different industries and the various risks that could appear if AI is not handled properly.
So the last concept we're going to be talking about today is sampling bias, where there's a bias embedded within the sample that the AI is trained on. And this occurs when the data collected to train or evaluate the AI model is not representative of the actual population. So looking at the diagram, there's a small sample that we trained the AI on, but it is not an accurate representation of the actual target population we're creating the algorithm for. And in this case, AI learns the patterns that do not generalize well, leading to skewed or unfair or inaccurate predictions. And if we draw conclusions based on the use of this AI system, we might be reinforcing barriers or continuing to marginalize some of the already underrepresented groups.
To wrap up the module, let's take a look at a real-life scenario. Let's say you're tasked to study how low-income families access online educational resources by distributing a digital survey through all the school district email systems. Now, this may seem like a good approach, but this actually introduces an undercoverage bias, as there could be families that have limited internet access, who don't know how to use the internet, or may not be fully stable in housing and won't be able to check school emails or lack access to devices. As a result, the data that you collect will be more skewed towards families that are digitally connected and families that are stable in their living situations. This may not accurately reflect the challenges faced by all low-income households. Therefore, any conclusions drawn from the study may overlook and not take into consideration the most vulnerable students and the people that need the most help, reinforcing educational disparities and excluding the voices of those that need the most support.
Well, that wraps up our module on bias and fairness, and our next module is going to be on safety and robustness.
Now we're going to take a look at an interactive notebook that we prepared for you, go through some technical examples and walkthroughs, and then we'll see you all for the next episode of our AIE curriculum. Thank you. So, thank you for listening to our presentation. Now we're going to quickly go over an interactive notebook that we've prepared for you that is going to cover bias and fairness in AI. We're going to try to understand what bias means in context of machine learning, learn how fairness is measured, and then just do some interactive exercises. So what is bias in machine learning? This is pretty much when a model systemically makes unfair decisions for you. Sometimes it's come from data, sometimes it's come from labeling. And if the data isn't diverse or fair, then the model likely won't be either. We're going to start off by simply looking at our libraries that we've imported here. And just as a heads up, we're going to be working with a small, entirely made up data set throughout this activity. This data set is not realistic and it's not representative of what you find in a real-time production environment. And we are going to be intentionally putting in biases just to show what results could come. To prepare the data for modeling, we are going to create a Panda data frame that you guys have worked with before, and we're going to input 3 different features: experience, gender, and whether someone was hired. The goal is to use this data to predict hiring decisions. We have the years of experience listed in an array. We have 5 males and 5 females, and then the 0 represents that a person did not get hired, and the 1 represents a person did. And so as you can see, only 1 female got hired, even though they had a really high experience compared to the males, where 4 of them were hired. And to prepare this data for modeling, we are going to convert the gender column, which originally contains male and female as strings, into numbers. This process is called encoding, and this is necessary because machine learning models don't work with text. They don't understand strings. However, they do understand models and numbers. So we're going to use 0 for the males and 1 for the females and store this in a new column called gender encoded, which you can see we do right here. Now what we're going to do is we're going to visualize this data set. We're going to see what happens when we plot this out and what kind of appears. We are intentionally adding some jitter or some extra numbers to these points to separate them so that we can see what exactly appears. And as you can see, the blue dots represent males, the pink dots represent females. And the blue dots are a lot more representative in the hiring yes category. You can see that 1 means a person was hired, a 0 means a person was not hired. And even though the female candidates had the same number of experience as the male candidates, a lot more of the male candidates got hired. As you can see, they're higher up. There's only 1 female candidate that got hired versus the 4 males that got hired in general. And so this shows a bias that could appear in hiring decisions. Now we're going to train this model. We worked with logistic regression models before, and we're going to follow the same process that we did in the last module. We're using the train test split function. We're going to train it and fit it on our training data, and then we're going to make predictions. And what that leads to is an overall accuracy of only 33%. So this shows that our model isn't really that good when it comes to predicting outcomes, and we need to make sure that our data is less biased and it's able to capture the general outcome of what we want before we actually start to implement a logistic regression model. This next exercise is meant for you guys to explore group level fairness and modify the logistic regression example to calculate the false positive rate for each group.
Okay, after this activity, now we're going to be going over measuring fairness between groups, which is based on an accuracy rate over a data set. And in this piece of code we're looping over the results array and then comparing the predicted number with the actual number. And then we see that the accuracy for females was 0.5, whereas the accuracy rate for males was 0. And that means that the model failed entirely for male candidates with 0% accuracy, and got every prediction for males wrong. And this also implies that the model is biased, likely due to the way training data was labeled, and is not making fair or consistent decisions across the groups. And speaking of labels, now we're going to be going over an example that showcases label bias, where we will have two identical inputs that will be labeled differently based on group membership. And so we have imported a pandas data set called PD, and then we'll populate this data set with three different parameters. Okay, so we have, let's say, text, and that will be, let's say, all individuals are smart and hardworking. Okay. And we'll have 4 individuals in total. And the order could be male, female. As we said in the beginning of the module, the hiring, so we'll define hiring on a binary basis where 1 stands for being hired and 0 stands for being unemployed. So, wait. And the first person will be hired and the second one will not. We will want to print the results too. These metrics. And then we see that even though all of the individuals are smart and hardworking, based on the gender, the labeling of the individuals have changed, which means that the model we had was biased.
Now we can wrap up our interactive activity by talking about correct sampling bias. If your data set is imbalanced, for example, if there's a lot fewer examples from one group, you can give underrepresented samples higher weights during training. This helps the model treat each group more equally, reducing bias caused by unequal representation. To do this, we can use a function from scikit-learn called compute sample weight. We have our data frame that we have categorized before, and as you can see, there are 90 males and only 10 females. What we can do is that we can call compute sampled weight and pass in a parameter called balanced. What that will do is that it will balance out our data so that the males and the females are being represented properly. Now from there, we can see that we call our logistic regression, fit the model to the data that we have, and we can train the weights to correct the underrepresentation. In some cases, simply removing a sensitive feature like gender from the training data could reduce bias. This example shows how to train one model with gender as a feature and another without it, just to see how it affects model behavior. We can do that by first creating our data frame that we've done 3 or 4 times now in the activity, where we have our experience, we have our gender, and we have the amount of students or people that were hired as well. From there, what we can do is that we can create our column that we've created before for our gender encoded. As you guys remember, we are not going to be able to pass in text into our model, so we need to convert this into a number so that our model can understand it. So we can do this simply by setting males to 0 and then setting females to 1. Cool. So now what we can do is we can create our different sets that we want, one for gender and one without gender. So we can create our X with gender and set that to the experience column from our data, but we also want to make sure that the gender that we encoded is also in there as well. Now we can do the same thing, except now in this situation, we don't want the gender to be associated. So we can do X without gender, take away gender encoded. So now the only thing we're looking at is experience. And the last thing that we want is whether to see if these people were actually hired or not. Now, what we're going to do is we're going to create our models, one with the gender and one without the gender. So we're going to do model with and set it equal to the logistic regression and then fit that to the data that we have with the gender. And then we're going to map that to what results ended up with them. Now we're going to do the exact same thing as we did here, except we're going to do it without the gender. So if we have model without, we set that equal to logistic regression, do the same process as we did before, except in this situation, we are just going to map it to our data without the gender. Now from there, we can simply print model trained with and without gender to compare impact. Now once we do this, this should successfully come out with both of our models being trained. And now we can take a look and see what exactly came up. So if we do the predictions with model underscore with dot predict, and then we pass in the with gender data. So now we're going to be making predictions based on the model with the gender. Now we also want to make predictions with the model that we created without the gender. So by doing this, out gender, and then now we can just print out both of these to see what exactly came up. So we can print out the predictions with the gender. And then we can also print out the predictions without the gender. Cool. So as you can see here, we have predictions with the gender that you see above, and then we have predictions without the gender below. They are a little different, and we'll see what exactly is the beauty behind this in just a second. Cool. So now I want to take you through the last part of this activity, and this may seem a little counterintuitive at first. We're going to calculate the accuracy score, and based off of what we talked about, we should see an accuracy without the gender as higher. But as you can see, the accuracy with the gender is coming out to a perfect score. Accuracy without the gender is at 0.9. Now, in a real life setting with a huge data set and with a lot more moving factors, there's a very high chance that your accuracy without the gender, without this bias, could lead to a better outcome. But in this situation, there are a few things that this suggests. The first thing is that the model with the gender uses gender as a predictive shortcut, which pretty much means that if including the gender encoded feature gives perfect accuracy on the small data set, it may be because the model has learned to associate gender directly with the outcome. And that's problematic when gender shouldn't be a deciding factor in hiring. The second thing that this suggests is that the model is overfitting. We talked about overfitting in the last module. And if past hiring in the data disproportionately favored one gender, the model with access to that feature learns the bias and replicates it, leading to high accuracy but also highly discriminatory behavior. The last thing that I suggest is that removing this gender reduces reliance on bias signals. The drop in accuracy from 1 to 0.9 when removing gender could mean the model now focuses on true predictors like experience. While accuracy does drop slightly, the model becomes more fair because it no longer uses a sensitive attribute in its decision. Hopefully you guys enjoyed this activity. There is a fun little exercise we have for you guys at the end. We hope you guys go through it, play around with it, and discover how you can modify this data set or model to reduce bias.